Okay, so we talked about dynamic programming approaches and applying the Bellman operator directly to determining your value function or your state action function based on knowledge of the world. We talked about Monte Carlo and TD learning or temporal difference learning based methods when you don't know the world, but in one case it's only episodic that you can do with Monte Carlo, but with TD learning you can do this at every iteration. You are getting closer and closer to a particular value. Well, in the last lecture, we talked a little bit about Q learning. In the context of Q learning, what you're doing is you're updating your Q value. It's an off-policy approach because what you're doing is at every iteration, you're now applying your expected maximum Q value to your TD target, and you can kind of update that iteratively. So in other words, we're in a state, we take an action, we see a reward, we see a new state, and we update our Q function accordingly based on our previous value. Now, I was already starting to talk a little bit about how we can start to what if we're in a situation where we don't know the number of states, we don't even know anything about the state? How do you encode the state, or you want to encode the state in a kind of complex way? For example, you're playing an Atari game and you have an image and you want to encode that into some kind of state. How do you do that? Well, one way is you can now kind of take these Q networks, these Q functions, and turn them into neural networks. And so one second, let me move myself again, calling out the Lillian Wang blog post that kind of touches on this, and a lot of these materials were pulled from. Highly recommend using that as a reference for a lot of these slides, and just in general, it's a great thing. So as we talked about last time, Q learning should look exactly the same as here. This is literally the Q learning function. And so what we're going to do is we're going to consider the Q function as a parameterized deep neural network. So in this case, what we're going to do, we're going to have a Q function given a state action input, parameterized by this set of thetas that we're going to be learning, and this is just going to give us a value, a real value. And now we can just define a loss function, right? So the loss function in this case is the expectation over SARS from this distribution. And I'll talk about this in just a second. What's this UD all about? And keep in mind, remember that Q learning is an off-policy algorithm, meaning it's operating on data from a different policy, not necessarily the one that we have. And so the loss function is going to be the expectation of this reward plus this discount factor gamma times the Q function of that new state, right? The new state that we've seen, and a new action, in this case, the best action, right? This is the this is Q learning. So we're going to take the best action that we can take. It's sort of that argmax. That's what that means there. With this parameters minus, I'll talk about what the minus is in a second, minus QSA squared, blah, blah. This just looks, if you look at it kind of with a squinty eye, you can look at this and say, oh, that looks just like supervised learning, right? This looks like the L2 norm between a target and the expectation. So that's actually why we have that theta minus there. The theta minus is to ensure that we have a stationary distribution. Otherwise, this Q function is going to change every single time this theta thing is. So we're actually freezing the thetas. Periodically, we're updating them, but for a while, we're just using this target as a stationary target, and then every once in a while, we're going to update it based on this thing. So we're just going to cut and paste that in there. So another thing that might be annoying, like what is this UD? Well, that's a uniform distribution over what's called the experience replay memory. So what we're going to do, instead of looking at the data that we're seeing, we're actually going to look at the data that we've seen and just sample it randomly. And so that's kind of an important thing. This gives you, again, remember supervised learning and unsupervised learning, this just gives us a mini batch. So we take a mini batch of all of the different tuples that we've observed, right? These state, action, reward, and then new state tuples. We sample some number of them, and then we calculate this expectation. That gives us a loss, right? And now we can take a derivative of that loss and the way that or the gradient of that loss. And how do we take the gradient of that loss? Well, easy, right? This is the reward is a value. So that's the gradient 0. This is just a value. Again, remember the theta minus is not, it's a stationary thing. So this is just a value. So that turns into 0. So we end up just taking a gradient of this Q value function, parameterized by this set of thetas, which happens to be, it's a neural network, so you don't really care. You just plug it into your auto gradient thing, like PyTorch or what have you, and you get the gradient, right? Or you can manually do it yourself or what have you. If you have a linear combination, like you can use a bunch of different parameterizations for this network, and so at that point you can just sort of do whatever makes sense for you, right? You know what the derivative is, the gradient is based on all that. So yeah, that's it. And this will improve until convergence if you do that. So one thing, as I mentioned, right, we periodically update this theta minus, and that's because this just allows us to keep it a stationary distribution, but we do have to update it periodically. So like that's a hyperparameter that you may want to kind of deal with. So the DQN network, DQN algorithm is one of the first sort of examples of this, where you can now have a Q network, and then you're essentially updating it by Q learning, and the Q network is a neural network. So this is the algorithm here, and let's go through it because I think this is a good way to break down what's actually going on here. So we initialize the replay memory D to capacity N. So this is just what's our mini batch, or what's our capacity replay memory. And you can already hear like, well, there's a bunch of little gotchas here, like what do we throw out and what happens when it gets full, whatever. We initialize our Q value function Q with a random weight. So we just, start off with something. And we initialize our target action function with weights theta minus, or just theta. So we're just copying it here. For our first episode, through episode 1 through M, we do the following. We initialize the sequence, S1 is equal to X1. We process the sequence, phi1 is equal to phi S1. So phi1 in this case, by the way, is a way to represent your state. So this is from the DQN paper. The DQN paper was about Atari games. And so in this case, the state was a bunch of frames. There were actually 3 progressive frames of video, and that was put through some kind of neural network to give you that state. So this is a little bit, we'll talk about this like in the next set of lectures because really kind of tackle some of these reinforcement learning algorithms with in the deep learning context. But that's what it is. So actually phi1 is our state representation. We're encoding the state into some kind of thing, and that is learned jointly with everything else that we're doing. But if that's confusing, don't worry about it so much. We'll talk about it later. So we start off with this S1, that's from our X1, and then we encode it in some way. Now for T from 1 until termination, so T will be different for each episode, keep that in mind, but it's going to be essentially from 1 until the end of the episode. We select some random action AT with some random probability, or we select AT being argmax of Q given the state and the action parameterized by this theta. So remember, this phi is just an encoding on our state, and this Q function is going to be, and these first 2 lines is just E greedy, right? With some E probability, which is small, like 5% of the time, we're going to choose some random action. We want to explore a little bit. Otherwise, we're just going to select the action that maximizes our Q value function, which is just a neural network. So in this case, we're taking the state encoding, and we plug it in, and we check all the actions. Say we only have 10 actions. We run this thing 10 times, and we choose the action that has the maximum value. So that's how we choose AT. We take that AT and we plug it into our emulator, right? And then we get back a RT and a new image, XT. So that's just like a new state, right? And so now we have ST is equal to T plus 1 is just ST, AT, XT plus 1, and pre-process this again, and we store this transition in D. So now we're saving our stuff in there. Again, this is a little bit of technicality around how DQN worked, right? Because you're seeing these frames, and the encoding for state was not just one frame, it was multiple frames. Because in a game like in Pong, you want to know about movement. You want to know that the ball is moving. You want to know that the opponent's moving, whatever. But the idea here is you're saving this, right? We're appending the state plus the new thing, and we're also encoding it. Now we store that in feet, like our last state, the action we took, the reward we got, plus the new state that we saw afterwards. And we're only dealing in the encoding because we only really care about that. That's what's getting plugged into our DQ, our deep Q network. And so now we've done our iteration. We've done the thing we're supposed to do, and we sample a random mini batch of transitions from D. So this could be who knows when, right? It could have been 2 years ago, it could have been last night, it could have been 5 minutes ago. It's in the past, can't be in the future. We don't know the future, but it's some random set of them. So they could be all over the place. And now we set Y. We set Y to be, and why is a Y? Because we have this supervised learning task that we're trying to do, right? If we terminate at the next state, and again, keep in mind this is the sampled states. If we terminate then we just get the reward of that state because there's nothing. The value of the next state is 0 because we're done. Otherwise, the yj of that state is going to be the reward plus the epsilon times this q target. And keep in mind the target is with frozen weights, right? This theta minus, right? We've copied them. We'll talk about when we copy it again, but that's how we state the value of the next thing. And now we perform a gradient descent step on yj minus our q function. This is just this equation here, right? So it's just a little bit broken up because we have these neural networks in the way and all of this stuff. And every c steps, we literally copy our q value function, our deep value function into this new one, this target one. So C is just a hyperparameter. You can see there's a lot of nuance here, like what's C going to be, right? How big is D going to be? What is this phi thing? And we'll talk about a lot of those next week. But yeah, this algorithm actually is pretty straightforward. It's not different at all than this Q value deep Q learning, or sorry, no different than just the Q learning algorithm, except we're using deep neural networks to do this. We have to encode these images into states and create some kind of representation there. But I think the fundamentals are actually really clear. So this is, I think, one of the first times that deep learning was used in a reinforcement learning context. I encourage everyone to read this paper. It's just the DQN paper. It's a pretty easy read overall, and it's quite impactful. Just a heads up, you want to implement this for your project, that's a great project, right? This is a good thing to do. So with that, this is great. We see the supervised learning task here in the core, in the heart of DQN. There's another class of deep learning algorithms for reinforcement learning, or what's called the policy gradient. So I'm not going to go through the proof here because the proof is quite involved, but if anybody wants me to, I'm happy to put together a separate lecture on the proof because it can be quite long to really go through it. But the idea, the intuition behind the policy gradient is that, so we have this J, this sort of value function we're looking to maximize. This is if it's a little bit confusing, this is just a different mathematical way to formalize the value of a particular set of parameters, right? So to kind of like try to translate this, right, over all states with this distribution over a particular policy parameterized by a set of thetas, theta, right, multiplied by the value of that state. That's the cost. So basically what we're saying here is we have some kind of policy. The policy is parameterized by a set of thetas that we need to learn, that we want to learn. And based on that, we're going to see a distribution of states. So the policy defines this arbitrary distribution of states that we're going to see, right? This kind of makes intuitive sense, right? If I have a policy of only taking a left, when I get to a corner, I'm never going to see what's on the right. So that's going to define my distribution moving forward, right? And so based on all of the states that we see, right, the likelihood, this is just a probability distribution multiplied by the value. So this is just an expectation, right? Where the value of a particular set of thetas is defined as the expected value of all the states we're going to see the value of them, of the value of all the states that we're going to see, and this is just the distribution of those things. And on the right side of this equation is just that exploded out a little bit more, the value function being defined as the distribution over all actions given a particular state times the Q state action, the state action value of that thing. So this is just the right side's more of a way to think about how this equation, this proof, is proved out. So skipping a few steps because I think this is a little bit beyond the context of this course, you can kind of, well, if I have this cost function and I want to optimize it, how do I optimize stuff? Well, I take the gradient and then go in the direction I want to go uphill, right? If I have my cost function, I can take well, which way do I go to improve? If I can do that, then I just follow that direction until it goes to 0. That's how we do optimization, right, of these kinds of functions. Well, yada, 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 if you do that, you end up here in the bottom, which is the expectation over a particular policy of the gradient of that policy times the Q function. And this is like a pretty profound thing, right? Like, it's basically saying if we can take a gradient of a policy, then by taking the gradient of that policy, we can actually improve the value function, or we can improve the expected cost just by way of following the gradient of that policy. But that's pretty cool because we know how to define these policies parameterized by these thetas and by these parameters, and we know how to take the derivative of them because they're neural networks. So if we pop in this function, this complex function approximator into here, parameterized by these thetas, we essentially can just we could just improve it. And now you multiply it by the state action pair, which we can just estimate because we've been doing that this whole time, right? We can just calculate it tabularly. We could use TD learning, whatever you want. And over time, this is guaranteed to get us to a better cost. So there's a number of these algorithms. This is the policy gradient concept and sort of the theorem. And there's a number of different algorithms that use this theorem. I think the classic one that most people kind of know about is what's called reinforce. And this is one of the simpler ones. We'll talk about more of them in the future. There's a number of these. But reinforce, I think, is the simplest one. And we essentially just update the parameters of our policy based on Monte Carlo sampling. So we take samples and we then calculate the derivative of the policy, and then we apply that. Sometimes we use a baseline. A baseline just kind of reduces the variance of the gradient estimation. And the way we can do that is, for example, we could use something like the advantage function. The advantage function is defined as the Q state action pair minus the value function. So it's like I'm in a particular state, and the value of taking a particular action in that state over the current state, that this is the value over it, right? So it's like, what's the value? What's the advantage of taking one action over another? And so we can use that as a baseline. But let's go through the reinforced algorithm because it's really simple. You initialize these parameters at random. You generate an episode. So again, this is Monte Carlo, and so this is an episodic setting, which is one of the limitations of this algorithm. And then you go through the time steps t, and you estimate the return since time step t, right? And now you update your parameters multiplied by this thing. We don't even use the Q function here, right? Like, we're essentially multiplying it by the return times this discount factor with this learning rate, and we take the derivative, the gradient of the logarithm of our policy. And the policy in this case is a deep neural network of some kind, where we're plugging into it a state, and it's giving us an action, and yeah, that's it. I'm not going to go too deep into implementation here. That'll be for next time. But yeah, this is it. This works. Now, one other kind of algorithm I want to introduce before we kind of cut off, and it's going to be really quick because we'll talk about these more in the coming lectures. But we talked about policy gradients, And you can kind of see policy gradient is a little bit like different than deep Q learning, right? In one case, we're estimating the Q state action function, in the other, we're estimating the policy. And even in the policy gradient theorem, you can kind of see this Q state action, this Q value function kind of hanging out there. It's like, wait a minute, how do we get that? How do we estimate that? So actor critic is a kind of way to marry these two ideas together. Let me move myself over here, right? In the case of the critic updates the value function, either the value function or the Q value function, and this is done as a network that is parameterized by a set of thetas that is separate from the actor network, or the policy network that is defined by a set of parameters of actor, is basically updating the policy. And the intuition kind of is that you've got a actor that's trying to improve their performance, and then you've got a critic kind of on the sidelines saying, well, what you did was actually good or bad, right? And so you have this push and pull. And so this algorithm, actor critic, is a very popular one, and there's even things like what's called soft actor critic. We'll talk about these next time for dealing with different kinds of action spaces and so on. But let's go through the algorithm because I think it's good. It's helpful to kind of break these things down. So like before, we initialize our state, our theta, and our w at random. What's w here? Oh, this is the w in this case is the parameter of the critic of the Q value function. So it's a little bit confusing. So like w is the weights of the critic, and the thetas are the weights of the policy. So we start off and we sample an action based on our state that we've been given, and on this just uninitialized policy network. And now for 1 through t, and t here is, by the way, this is an iterative thing, so we don't need an episodic setting. We're going through 1 through t, which is the end of our episode, meaning so we're iterating on our current episode, and we may die, and so that's considered one epoch, right? But we can do this many times. So first off, we sample a reward given our state and action that we've taken, and so we are given a reward, and we get a state from this world model, which we don't know, by the way, right? Ultimately RSA and PS prime SA are not known by us. The environment provides us with these values. Now, based on that new state and that new action, we now take a new action. I think this apostrophe is incorrect, but either way, we sample a new action. Now, based on that, we update our policy parameters. This is just Q learning, right? We take our theta plus our learning rate, a policy learning rate of the Q function times this is just the existing Q function. And again, keep in mind, the Q function here is a network, right? So we're just plugging in the state and the action given a set of weights. So that's just going to be a value. And we multiply that by the gradient of our policy, given by these parameters, theta. So this is just backwards propagation on our policy times a forward propagation of our Q network. And we update now the policy's thetas as a result per the learning rate. Now we have to correct the action value function at time t. And what we do that is we do this with this TD target, right, of the R that we've the reward that we saw plus the Q value function of the next state and action minus the current one, and we use that to update our value function parameters as seen below. And that's it. And this is, by the way, right, just the sorry, if you take this and you put that out here and you like plug this in, it's just sorry, I'm getting a little mixed up because I don't remember exactly where this form comes from. So I might leave that for next lecture to dig into it. So I apologize. But ultimately, you can kind of imagine this being plugged into here, and that just being the sort of supervised gradient of the TD target. So if you were to take this derivative, you would get this. But I'm not going to get myself in trouble. I'll talk about it later. But this is the update for the weights for the critic. And now you update the action and the state based on these new ones, and then you rinse and repeat. And so what's happening here, right, is your new Q function, your new Q network parameters are being used to update your policy, and your new policy is being used to update your Q function. Because ultimately the reward that you see is coming from the policy that you select and the action that you take, as is the action that you're plugging into this Q network as well. So this is sort of the push and pull of this algorithm, and it's shown to work a lot better than just reinforce on its own or just deep Q learning. So yeah, that's about it for this set of lectures for this week. This is not necessarily an exhaustive list of different reinforcement learning approaches, right? But is definitely a good introduction to a lot of the different things. And then next week, we'll start to dig into sort of the some deep learning papers, like we'll go a little bit deeper into actor critic, into some of the other deep learning approaches, as well as soft actor critic and some of the other things that are interesting. And then we'll kind of be done with the reinforcement learning stuff a little bit. But yeah, thank you. Sorry for if I'm this stuff is there's a lot of little nitpicky differences, and I try to do my best to make sure that I kind of cover all the gotchas, because I'm still it's it's always like there's like a little twiddle somewhere, and you're like, is that supposed to be there, or is that a core part of the algorithm? So just making sure, if any of these subjects are interesting and you'd like me to go into them deeper, please, as always, comment on the Discord, and I'll do my best to record some new lectures. Cool. Thanks, everyone. Bye-bye.